I apologize for not being there. It would be nice. On the other hand, life is chaotic, so that's the way it goes. I will happily stay around as long as I can and field as many questions as I can. I understand you have other things that you want to do. And I will apologize if I ramble a bit. I do tend to go on, and it's slightly weird being on the end of a silent video call. So we'll see how it goes. But there are no questions to, sorry, I'm losing a button here. There are no stupid questions, is what I'm trying to say. We just work through things, and always we try to answer all the questions there are. There are really no stupid questions. So what I'm going to talk about is an instrument we're building for the William Herschel Telescope. In fact, we've built it. It's there. More on that later. It's clearly not something that I've done by myself, so I have to give credit to a lot of people where credit is due. And it's a collaboration that spans Europe through a whole series of bilateral agreements, some individual scientists working within the consortium, a university in the US, the National Optics Institute in Mexico. We spread quite far and wide. We're just getting Lithuania on board at the moment. So it's a big program, and we hope to get a lot out of it, which I'll show you more about as we go forward. Now, an apology. Today is a special day for some people, and sorry, this is not moving forward. There we go. My daughter kind of insisted that I put something up about Star Wars today, so apologies for this, but there you go. By way of a little bit of brief introduction. This is just a quick idea of where we go. So all of this will become more apparent, but I said I would do that, so there we go. Okay, introduction. So I'll begin with the motivation for how we got into doing big surveys in astronomy. I think we've always done this at some level, but I'm going to go back to the 1960s, and a couple of people in the US started looking at the Lick sky survey plates and counting galaxies. And they counted galaxies by eye in 1 degree cells. And this is the map that was produced 10 years later when computers caught up and were actually able to produce the map. This is the introductory page to a famous book by Jim Peebles. It's a really nice chap. And so this is 800,000 galaxies in the northern galactic hemisphere. And immediately as you produce this map, you see tremendous structure there. Somebody re-reduced it and redid the counts in 10-arc-minute cells, and you see even more detail and more structure. But yet you also see other things. So you see that this is falling off at the edges. That's just the absorption in our own galaxy. And it's not a perfect map. If you look very carefully, you can even see the plate boundaries from the individual sky survey plates, because the magnitude limits of the different plates are slightly different. So it's a bit hit and miss. And many years later, my colleagues and my supervisor, in fact, when I was a PhD student, were working on this project to digitize in much more detail the UK sky survey plates. So this is a map that I produced of 4.5 million galaxies across the southern sky. The scale here is that this is 1 UK Schmidt plate. So this is 6 degrees on a side. So this is, if I have my numbers right, this is 4,300 square degrees of the sky. And I've colored it so that the faint galaxies, or the faint slices, this is just the density map, the faint slices are red, the medium bright slices are green, and the brighter slices are blue. So you can see there's nearby superclusters and there's very distant superclusters, but this web of structure is everywhere. And so that's imaging. And you want to go deeper. Taking pictures is easy. This is a bit of one of the Schmidt plates from the Northern Hemisphere survey. This is the Coma cluster. You see an awful lot of interesting things, but you see many, many thousands of targets there that are ready to be followed up. You can go deeper, you can get higher quality imaging, and you can get colors. And immediately you get colors, you start to see that galaxies really stand out. Galaxies have different structures. Stars are fairly easy to separate because of colors at some level. But much better is to get spectra. So the motivation is to take those pictures and try to understand what's really going on there by getting spectra. So these are just a couple of galaxy spectra thrown in. These are sort of classical ellipticals, passive spirals, and then active spirals, and really active irregular galaxies with ongoing star formation. So here you see absorption features. This is calcium H and K lines. This is the G band. This is H delta, and coming up to this is H alpha in absorption. Sorry, this is H alpha in absorption. This is sodium. And then in emission, this is oxygen. Again, you can see the H and K lines and the Balmer series, and then oxygen, oxygen, sorry, H beta, oxygen, oxygen, and then H alpha and the nitrogen lines that are sort of merged in with it either side. We'll see a lot more of those later, and the sulfur lines, and just a great difference in what's going on. But spectra tell you many things. So with the spectrum, we can get velocity, or in the case of a galaxy, we get redshift. We can get dynamics, so we can get the dispersion of that velocity, the width of the lines. We can get the composition, we can get the stellar chemistry, surface chemistry of stars. We can get the stellar populations for galaxies by decomposing the spectrum into different spectral types of stars. And we can get things like ages and mass and size and evolutionary history for galaxies and even for stars. But we need a lot more effort. So we need more optics. Because we need more optics, we typically have lower transmission. To put that in context, a good imaging telescope will give you about 65% throughput. A very good spectrograph will give you about 35% throughput. Probably the best quality spectrograph you can make will give you about 30% throughput. So you're also dispersing the light, so you have fewer photons landing on your detector pixels, and you need longer integrations. You also need more pixels per object because you're spreading all the light out, so you can't observe as many objects at the same time with the same price. So this is the kind of breakdown between spectra and imaging. And doing this one object at a time with spectroscopy is possible, but it's very, very slow. So again, we go back in history to the mid-80s. And this is something called the CFA Redshift survey, where they started taking all of the galaxies, basically the galaxies in that map that I showed you right at the beginning, and measuring redshifts for them. And then when they'd got enough, they started plotting them out, and they were horrified with what they saw, because first of all, they saw this big structure going across the sky. And then they saw this huge feature, which looks like somebody's pointing at you. You're here as the observer in the center. Looks like somebody's pointing at you out of the universe. So this is actually the Coma cluster. And this wall of galaxies is real, but it's greatly enhanced by systematic effects in the selection of the targets. And they took a lot more spectra. And you see the wall is even more enhanced, but you see more and more structures coming in here of big clusters. And now the little stick man that they called it is almost buried. It's still there in the middle, but it's almost buried. So it's very slow. That took about 5-6 years to produce just that many spectra. And as a consequence of that, people began to evolve much more dedicated, complex instrumentation to allow simultaneous spectroscopy. And the conclusion of that from where I came in was we went back with an instrument called the 2DF instrument at the Anglo-Australian Telescope. And in the 1990s, late 90s, early 2000s, we put together this survey from the APM Galaxy survey. So this is now 220,000 redshifts, measured about 400 at a time. So maybe 3,000 a night if you're lucky. But the structure's there. And the interesting thing we see here in the survey is that this is just the magnitude fall off as you go further out in the universe. So we lose things because we have a magnitude limit. But within this region, we're not seeing structures dominating on the size of the survey. So we have what we used to call a fair sample of the universe. And indeed, this was very powerful. We used this to determine the matter density of the universe, which is a critical ingredient to the current cosmology that we understand as the concordance cosmology and the existence of dark energy. So this was great to do. And this was now, I hate to say it, this finished 20 years ago, so it's quite terrifying. So now I'm going to wind forward, and I'm going to wind forward to the present day. In 2013, ESA launched a satellite called Gaia. I know there are people in Surrey working on Gaia data, so it gets everywhere. And Gaia is an astonishing instrument because it can measure the positions of stars to an accuracy of about 5 to 10 micro-arc seconds. Now, it's hard to imagine what a micro-arc second is. Somebody coined the phrase picoradian, which is quite fun. But the way I always think of phrasing it is that if we had a telescope on the ground with the resolution of Gaia, that angular resolution, you wouldn't just be able to say that we went to the moon because you can see the flag. You would be able to read "Made in China" off the boot print in the dust. So that's truly astonishing. That's the kind of resolution that we're talking about. And what you get from that is you get excellent distances from parallaxes. So you look at stars from either side of the Earth's orbit against the background, and you determine distances to very, very high accuracy. And you look at those stars 40 times over 5 years as the satellite orbits. And so you also see how the stars are moving across the sky with proper motions. So now we have distances and proper motions for about 100 billion stars in the Milky Way, which is kind of scary. And it's interesting because we have the motions, and we can begin to build up a real picture of how the galaxy is moving, how stars are moving within the potential of the galaxy. And you can begin to trace the structures that are going on there, and you can start to think about the mass assembly history, how the galaxy was built up. So this is a simulation, and this relates back to my comic introduction. So this is a satellite galaxy falling into the Milky Way. And this is just a very coarse simulation. We're now panning over the top of the galaxy. And as time evolves, that dwarf galaxy that fell in gets disrupted, and gets shredded, and gets spread over the whole sky. And eventually it becomes fully integrated to the point that you can't disentangle it. You can't see it anymore. But in velocity space, if you look closely, you can see that it's actually rotating backwards. So that's kind of cool on its own. But if you let it go further, it mixes to the point where you can't find it at all. It's just not there as far as you see it, apart from when you start to look at more detailed properties of the stars themselves. So in the early years of a galaxy falling in, you see streams. You see those streamers of stars spread out across the whole sky, and they're really very easy to detect in the outer halo. You can use them to probe the potential because you see how the stream gets disrupted as the galaxy moves around. So if it's just a simple orbit, that's one thing. But if you see complex structure in the movement of the stream, you learn more about what's going on with the dynamics of the Milky Way itself. So this is a classical picture. It's a bit messy because what you're looking at is an imaging survey, again, over two parts of the sky, the northern galactic hemisphere, the southern galactic hemisphere. This line around here is the plane of the Milky Way in this coordinate system. So there are no observations there because there's just too many stars to bother to observe. And this was really an extragalactic survey. But when people started looking at the stars, what they see is just in the photometry, and again, this is counts scaled by magnitude. Just in the photometry, you can see 1, 2, 3, 4, 5, 6. I think there's about 15 that you can obviously pick out if you go and stare at the data. Remnants of little dwarf galaxies that have fallen into the Milky Way. And these are quite recent. These are still out in the halo, so they're not fully merged. But this is a wonderful picture of what's been going on in the history of our galaxy. As you get closer in to the core, you need to go deeper. And the problem is that Gaia provides us with 5 coordinates in phase space, 3 positions and 2 velocities for an awful lot of stars. And it doesn't really give us radial velocities. It gives us some radial velocities for the very brightest stars. It's got a small onboard spectrograph. But for the reasons of the way that's designed, you can't do distant stars. Gaia pans across the sky, so the integration time for everything is completely fixed by the time it takes for that thing to cross the detector. And so you have a fundamental magnitude limit in what you can do with spectroscopy. And it really can't probe these streams. It just doesn't go faint enough. So to get full phase space coordinates across a large fraction of the Milky Way, we need a new instrument, and it needs to be on the ground because that spectrograph needs to be large. And what we'd like to do is measure spectra for 1 billion stars. But because of everything I said at the beginning, everything is just harder, and particularly real estate on detectors is hard. We have to compromise, and we have to say, look, what can we do? Can we do a 10 million stars, 5 million stars, that kind of order of magnitude? And how hard is that if you do them in a sensible way? And to put it in context of what we need to do, here is the sun within a schematic of the galaxy. This is the distance to the galactic center, so that's about 10 kiloparsecs. And this is the distance out to the edge of the halo, so about 20 kiloparsecs. And at this point, the proper motions that Gaia delivers are accurate to about 1 kilometer per second across the sky. And so to get meaningful phase space, we want to measure velocities to about 1 kilometer per second. So that's the kind of the guiding principle. And to put it in context of a spiral galaxy, the rotation pattern speed of a spiral galaxy is typically 220, 230 kilometers per second. So these stars are, we want to measure these velocities really precisely in terms of how things are moving within the galaxy. So we have to aim for this kind of velocity. That means we need a spectrograph with typically a spectral resolution, lambda over delta lambda, of about 5,000. This gives us something like 2 kilometers per second, and that's what we're aiming for. So that's the first ingredient of the instrument we have to try and build. If we can go to higher spectral resolution, we get chemistry. And so in terms of dimensionality, you can sort of scale up. You start off with positions, then you get parallaxes in 3D, then you get proper motions in 5D, then you get the spectra, and you go to 6D. And if you start to put in stellar properties and parameters and ages and chemistry, you can go up to 12 or more dimensions in parameter space of trying to disentangle the galaxy. So if you could do chemistry, that's great. But to do chemistry, you really need to go to a factor of 4 more in spectral resolution and get up to 20,000. And then again, you're cutting back on the magnitude limit that you can reach with your instrument. But it asks the question, can we build an instrument that will do both of these things? We'll do a decent spectral resolution out to the edge of the halo and a high spectral resolution that will allow us to study stuff in detail further in. Then we have some other parameters for what we're trying to design. So you need the largest field of view that you can accommodate on your telescope. And it turns out that there's a practical limit to this, because if you get too large, the fact that you're looking through a prism of the atmosphere means that your field distorts as you track. You won't ever see this on a small telescope, but the field starts off square, and then as you track down in elevation, it becomes trapezoidal. And it's difficult to deal with that when you're trying to take spectra for lots of things, because they're all moving apart. The other thing that happens, because the atmosphere is a prism, is we actually disperse the light. So we need to build some kind of compensation for atmospheric dispersion. That also changes as we change elevation. So it turns out that practically 2 degrees is a good compromise, and practically 1 hour is a good exposure time, because over that 2-degree field, you still have changes due to differential atmospheric refraction. So again, we're putting numbers into place for the sort of instrument we want to build. We'd love to be able to target many stars at once, and this is where fiber optics comes in. So in principle, you can take all of the stars in that 2-degree patch of sky, put a fiber on each star, repackage those fibers to the slit of a spectrograph, which is now off the telescope. So mass and size of the spectrograph is not really a limiting factor anymore. And you can package those fibers into the slit of what looks much like a classical spectrograph, but then it's stable because it's not moving around with the telescope. So some more parameter space. And now I'm going to take a step back, and I'm going to throw in something else. And the nature of what we do is that we try and do many things at once. So now I'm going to talk about radio astronomy and radio surveys. And this is the central part of a low frequency radio array called LOFAR, which is spread over the whole of Northern Europe. There's a dish down at Chilbolton in the south of England. We're quite heavily involved in this, but it's thousands and thousands and thousands of antennas spread across the whole of Europe. And what it gives you is very good angular resolution at low frequency radio. It surveys the whole sky. And again, it's found about 100 million galaxies over the whole sky, which is great. And at very bright densities, these galaxies are typical classical radio sources. They all look like this. They're beautiful. You go and study them. They're great. When you get down to the faint limit in terms of radio flux, everything is just star formation. So typically everything we see in the LOFAR galaxies is a star-forming galaxy, and it's sensitive to star formation at the rate of 1 sun per year, 1 solar mass of star formation per year, out to beyond a redshift of 2. So almost anywhere in the universe where stars are forming, LOFAR will detect a galaxy, which is great. It's wonderful. That's why you have so many galaxies. And if you select at low frequency, 150 megahertz, you basically detect everything that is star forming down in this region at all stellar masses, which is great. So sensitive to everything. But we don't know anything about these galaxies. All we know is that they're forming stars. So we need spectra to get redshifts. Back to the same old game, we need spectra to get redshifts, to identify them, to classify them, to know where they are. So this is typical different spectra for different radio galaxies. These map quite nicely onto what I showed at the beginning. And the nice star-forming galaxy spectrum has got lots of emission lines, which is great because it's faint, but you can get a spectrum very quickly, because if you have enough wavelength range, you can get a nice fingerprint from all of these different species, and you get a very good high-quality redshift. So what we'd like to do is observe a few million galaxies over the useful part of the northern sky. Go down faint, but signal to noise is a bit of a difficult game here because we're looking for emission lines. And somewhere buried in there, you have the possibility of finding the really bright high redshift things as well. So because you're trying to survey a very, very large area and look for everything that's forming stars, you'll pick out some of these really interesting things as well as the sort of run-of-the-mill things that you're trying to study. So we adopt something that we call a wedding cake strategy for this kind of survey, where we have deeper and deeper integrations in smaller and smaller areas. So you get down to targeted 2-degree fields at the end. And you can also go even deeper with another aspect of the instrument that I could talk about. Then there's another thing we can do as well, and that's that because we can build a spectrograph that will take fibers, we can reformat our fibers. So we can build something called an integral field unit, and we can do a bunch of fibers placed together on the sky and look at resolved spectroscopy of large objects. So nearby galaxies, we can actually study the dynamics within a galaxy. I'll come back to that later because it's what we did for our sort of first light target. But there's an experiment been running in the Netherlands to do blind neutral hydrogen surveys. And it sees neutral hydrogen in the very smallest galaxies. So if we can observe those galaxies in stars and star formation, we can start to disentangle what's going on. So this is a complicated picture, but this is the sort of stellar mass color diagram for all galaxies. And up here, we can look at quenching of star formation, tidal stripping, and disturbed interactions within galaxies. Down here, we can look at more normal galaxies, and we can look at how gas is flowing into star-forming regions and fueling the main sequence. So complicated interactions between neutral gas, ionized gas, and star formation, and the stellar population within the galaxy itself. We can try to disentangle all of that. So as I said, this requires something slightly more complicated in terms of reformatting of fibers, but I'll show you how we do that later. So if I put all of those things together, and this all came about because we had a meeting to discuss what to do with the William Herschel Telescope as it went into the next phase of its existence. It was built in 1983. We had a science meeting and everybody said, oh, we'd like to do, these main things, these 3 things. And I went, well, actually, you could build one instrument that could do all of these things if you think carefully about it and if you're prepared to commit to it. So to match to all of this, we need fibers that are about 1.3 arc seconds on the sky. You want to be on the sky. We want to be slightly bigger than typical seeing. Median seeing at the William Herschel is about 0.8 arc seconds. You don't want to be too big because then you're just dragging more sky background into your fiber, and it costs you a lot of money in terms of a bigger spectrograph. So we have a telescope with a big mirror and a prime focus capability. You can see here there is an old top end on top of the telescope that was used for prime focus imaging and spectroscopy. And a focal ratio for the telescope is actually very good for feeding fibers. If you feed fibers faster than about f2, you start to lose light because total internal reflection in the fibers doesn't work. If you feed fibers much slower than about f5, then you start to lose light because the light spreads out inside the fibers and it comes out at f2, 2.5, and it misses the collimator of your spectrograph. So there are lots of nice compromises, and a prime focus telescope at about f3 is really fantastic for this. So we're going to build an instrument that uses a 4.2 meter mirror. It has a 2-degree field of view. We're aiming for about 1,000 fibers of size about 1.3 arc seconds. To put that 1.3 arc seconds in context, that's an 85 micron core fiber. So the fiber is like a hair. Just bear that one in mind. We're going to do a couple of funny things with IFU modes as well to resample how we deploy the slit in different modes. And we're aiming for this kind of spectral resolution, but with a wavelength coverage as much as we can get in the visible over CCD wavelengths. So if you put those two numbers together, I'm talking about 16,000 spectral pixels for every spectrum. That's the kind of canonical definition of it. This is sort of what it looks like. So here's the top end of the telescope. We ripped everything out. We put in a new set of correcting optics to get that 2-degree field. We have to build a new rotator to support the instrument. And then we have to build something that will manage and handle all of those fibers. And this is about 2 meters cubed and weighs a ton just for the box. So the whole of this top end is 4.5 tons. And we control telescope focus by pistoning the ends of the spiders. We put 4 units on the end of the spiders with springs and cam-driven motors. We can control the position of that center section to better than 20 microns. And that's in tip and tilt and focus. We don't do active tip tilt. We're not trying to do fast imaging or anything like that. The spectrograph lives inside what was originally an imaging laboratory to be fed by the telescope Naismith focus, but we just feed the fibers down the telescope. So we have 36 meters of fiber, and then a spectrograph that completely fills that room. And again, for scale, this ring is 5 meters diameter. Somebody helpfully provided me with this photograph, which labels all the key points. So, and I was very pleased to see they'd labeled me as a key point. All of this came out of my head and has been quite fun to design. So I do feel kind of quite central to it. But here's the corrector. It's 2.3 meters long. The largest lens weighs 225 kilos. The instrument rotator, and then the fiber positioner with robots that will move the fibers around. And what you see here are the handling units that contain the fibers and maintain tension as we move them around so they don't twist and they don't snarl up, because they're horrible things to deal with. This is a little CCD controller for our guide camera, just so we can maintain acquisition. The corrector, for those of you who are interested in optics, we managed to deliver something which gives us better than half arc second images. And that's half arc second images with the atmospheric dispersion corrected. So that's polychromatic from 360 nanometers to 960 nanometers, all within half an arc second over the whole 2-degree field. That was quite a challenge. The biggest lens, as I said, it's 1.1 meters. I think at the time we made it, it was the second biggest lens ever made, and it was quite interesting. We have these 2 doublets in the middle of the optical system that give us the atmospheric dispersion. So they're doublets, and you drive them equal and opposite angles to correct for the prismatic effects. There's an A-sphere on this back of this lens, there's an A-sphere on the back of this lens, and then our focal plane is about 420 millimeters diameter. So that was a lot of fun building that. The optical system is such that the back lens of the corrector is actually inside the rotator system. And then we have a good distance between the back lens and the focal plane. So we can actually get an imaging camera sliding in here on a gantry, and I'll show you that in a bit. The telescope wasn't really built for something of this size. So the only way we can get this onto the telescope is to park the telescope at an angle, build the instrument into an angled holding frame, and just feed it into the space available. And then because the crane doesn't go all the way out, we actually had to bring this around and ratchet it back against the side of the dome to do the last bit of moving the telescope in, and then drop it in at an angle. And when you move up through the system, the front lens of the corrector clears this structure by about 5 centimeters. My very delicate robots clear this walkway by about 5 centimeters, and you have to come up and down and across and round. And somebody did a beautiful video of this to the theme of the original Tetris game, just to show you what it's like. So this is a fisheye camera because you can't see it otherwise. But so that was quite traumatic, getting that installed. Quick summary of the fiber positioning system. So here's the focal plane. Here are those tensioning units that I talked about. And then I have 2 XY robots with rotating gripper jaws on them that will pick up fibers and move them around. And they work together. They basically dance backwards and forwards in the focal plane. And they play a game of chess with 1,000 pieces to position the fibers to each configuration that you want to observe. This structure then rotates about an axis through here to bring it into the focal plane. And when this end is in the focal plane, there's another set of fibers here. It's back up here. So we take about an hour to position all the fibers, and we take about an hour to observe all the fibers. So the dead time is basically the time it takes to slow the telescope, and 2 minutes to tumble, because the mass of this structure is quite large. At the midpoint, we put a large bundle of fibers that's one of our integral field units to do resolved spectroscopy. So that's neatly in focus when this thing is at 90 degrees. And then there's an imaging camera down here, which we use for sky referencing, astrometry, focusing, many, many things. So that was built in Oxford. It took us about 5 years to build it. There's 100 kilometers of optical fiber inside it, which is kind of fun. And when you have it all built up, this is my last lens. So this is the back of my $2 million corrector. Here is the focal plane with all my incredibly delicate fiber optics in it. And this robot moves at about 3 meters per second backwards and forwards when it's scanning the sky. So you better get the spacing right here, otherwise chaos will ensue. The rope you can see is for a counterweight cable. Because we move the robots all the time while the telescope is observing, we cannot vibrate the telescope. Telescopes are very sensitive seismographs. And so every movement of the robot is perfectly counterbalanced by a moving mass going in the opposite direction. And it works really well. We don't see any motion of the telescope system from the robots moving. Just to give you an idea of what's actually happening in the focal plane. So these little magnetic buttons are 5 millimeters long. They have a fiber running through the core of them, and it ends in a prism. So the light will come in from this direction, and then it's bounced sideways into the fiber and then routed down the telescope. So I said the fibers were 85 micron cores. The positioning tolerance is about 1/10 of that. So we're basically aiming to position every fiber to better than 10 microns in the focal plane. With 1,000 fibers and 2 robots and 1 hour, that means I have 3.5 seconds to do this for every fiber. And I'm doing this with a robotic system that has a changing gravity vector while I'm doing it. So there's an awful lot of calibration going into working out exactly where to place each fiber at each time and how to get it in the right place. And it does work. You can put all the fibers down to typically 5 micron accuracy. I haven't yet quite got it to the point where they all go down first time. So there's a bit of an iterative process there. But there's a lot of calibration, and there's 12,000 numbers that I have to keep storing and updating and cross-checking. It's quite fun. When it's put all the fibers there, this is the 420 millimeter plate, and this is about 870 fibers on the plate. They're all backlit through the spectrograph, which is another challenge. So we have bright lights shining inside the spectrograph. And you see the ones parked at the edge of the field as well. So they're just waiting to be picked up. This is the array of, this is 550 fibers in an array for the big integral field unit. And we also have 20 really small little integral field units with 37 fibers each. These live inside the focal plane, so they're just bigger buttons than the other fibers. And that's the integral field unit in its sort of sideways position with its own CCD camera guiding it. So just what it looks like. The spectrograph is about 3 meters by 2 meters by 1.5 meters high. It has 2 cameras. I've shown them in 2 different positions because we switch between the low resolution and the high resolution mode. We change grating and we change the camera angle. And this works out very efficient. So the challenge was to design one camera that would do both of those modes. There's a single collimator and there's a slit exchange mechanism here with 4 slits fed into it. So it's a very complicated mechanism at that side working through it. And the dichroic is here between the red and the blue side of the spectrograph. So all the optics downstream are optimized for red or blue coatings. That keeps you inside an octave and gives you very high throughput. So the system end-to-end throughput in the red is actually about that 35% number that I was telling you about. And that's with 10 lenses in each camera. So quite a challenge. The spectrograph was also a bit of a pig to get inside the enclosure because it was shipped as a single unit. So it had to be lifted up and dropped into place through the roof. Really, again, really quite scary. Seems to have survived the journey quite well. And right now we're in the final stages of detailed alignment of the spectrograph optics. You can see the gratings. You can see that this is the red camera. You can tell it's the red camera because it's reflecting all the blue light off the coatings. So that's one of the red, that must be the low resolution red grating. And these are holographic gratings. So that, again, they're very high transmission gratings. I can say more about how they're made if anyone wants to ask me, but I won't go into it now. So June of last year, finally, we had everything in place. This is an old photo of the WHT taken from the mountainside with the dome spinning. And when we replace it with the new monster that we've put inside, it now looks like this. So it's really quite a change, quite dramatic. And as you can see, this really is quite tight in the dome, given where the crane has to go to move it. Quite a scale change. So I'll move on. I'll talk a little bit about what we did for first light. This is kind of a bit like what we did in our summer holidays, because we took some data and we played with it, and then we'd gone back and decided that we need to do a little bit more work. So we haven't done much more since then, but this is good data to talk about, and it shows how well the instrument works and what you can do with it. So we begin with the large integral field unit, and we take an out of focus star, which gives us a nice donut image. We use this to make sure that we know what the mapping of fibers in the array, as they're seen in the spectrograph, to position on the sky is. So if you reproduce the donut, you've got the mapping right. And then we checked it again with a very nice edge-on galaxy. I'll come back to the spectra in a bit, but this is the sort of thing you see at high resolution with the integral field unit. This is now the H-alpha line. And if you remember at the beginning, I showed you the 2 nitrogen lines were almost embedded in that line in typical low resolution spectra. Now they're very clearly separated. So these are the 2 nitrogen lines that are normally buried inside the H-alpha line. And the middle of last year was a very sort of auspicious time, because JWST had just come online and had just started to do things. And one of the first things they did was they produced this beautiful picture of Stephan's quintet. So this is a set of 5 interacting galaxies. The 5 are this one, this one, this one, this one, and actually this one. This thing is just a big foreground interloper that's at about 10% of the distance, so you just ignore it, but it's the thing that's most striking when you look at it. And James Webb showed you this beautiful image of what's going on here with a nice tidal tail linking this galaxy to this one, this pair that appear to be interacting, something happening here, a very interesting structure coming down here, etc., etc. And we also have it in X-rays from the Chandra satellite. And in X-rays, it's quite interesting because now this is all ionized gas. And that tells us something about what's going on. This is star formation. We'll come back to that when we see what we see in the spectrum. So 20 minutes on sky with Weave, and you get 600 spectra. There's some sky background spectra in there for subtraction. 20 minutes times 6 fills in all the gaps between the fibers in the array. And so now we have a resolved spatial resolution of about 1.6 arc seconds and a spectral resolution of 2500 in the low resolution mode, because these are big fibers. And we can just zoom into a chunk of that image. That's the whole of the red frame spread over 2 CCDs. We zoom into a chunk of this image, and now you can start to see that line. This is the nitrogen, hydrogen, nitrogen. This is actually the sulfur lines that I showed you earlier as well. It's quite bright moon when we did this, so the skylines are particularly bright anyway. But you see quite a lot going on. This is quite nice. And when you look up at the top of the slit, everything looks very well behaved. When you look down at the bottom of the slit, everything looks really messy, and yet the skylines are really quite well behaved. So we go digging into this down here, and actually what you find is that, yeah, these are all really messy. You've got velocity fields where the nitrogen lines are overlapping with the hydrogen lines in a single 1.6 arc second spaxel. And we couldn't quite believe what we were seeing when we looked at it. We didn't really know what to expect. We'd never seen this sort of thing before for this kind of object. And we went away and we looked at it with the high resolution mode. So now at a resolution of 10,000. And again, up at the top of the slit, everything's very well behaved. Down at the bottom, real mess going on. So what's happening here? Move back through the data. Again, that was still the low resolution. This is the high resolution, and this is now the bottom of the slit. So it's really complicated, really chaotic. So you can put those together and you can spread it out in wavelength in a cube. And this is now the 2 galaxies in the center and some of the structure around the edge. And you see, as you look in wavelength along this direction, different bits of structure light up in emission lines. So this is H beta 03. This is H alpha nitrogen 2. That's not a very easy way to look at it, though. So we put it together into a nice little movie. And here are the 2 galaxies interacting, and I'm stepping through in wavelength here. This is not time, this is wavelength. So I'm just going through the red arm, and as I step through, what you'll see is you'll start to see the nitrogen line come in regions where there's high ionization. This is star formation, and this is that wonderfully excited region that we saw in the Chandra image. Now this is H alpha coming in, it starts to really light everything up. So this is, again, a lot happening up here as well. The cores of the galaxies are quite boring at this level. And then you keep going through and you step through the second nitrogen line, everything lights up again. It's really quite spectacular. So you can then go into that, you can break it up into individual pixels, and for every pixel you get a spectrum. So in the cores of the galaxies, no big surprise, these are old stellar populations. These are like the things I showed you right at the beginning: calcium, G-band, H beta, magnesium. Down here we have star formation in the spiral arm of this galaxy, so H beta 03. And down here we've got these very complicated structures. This is now high resolution spectra, where everything is smeared out and interacting and just a bit of a big mess. And up here, yes, again, it's pretty horrible. This is low resolution where you see the sulfur lines. And what's actually happening, oh yeah, we did a nice funny face as well because you need a bit of humor here. So you can dive deeper and you can look at the velocity field. So this is now the typical velocity of this galaxy, the typical velocity of this galaxy. And this one, in some rest frame, this one is coming towards us, this one is moving away from us. But we can go deeper as well, because we can now look at the velocity field. So this is now the rotation of this galaxy. This is stuff moving towards us, stuff moving away from us. And this galaxy is rotating about this kind of axis. This galaxy is at a completely different velocity, is rotating about this axis. And then this is the shock starting to light up. So what's happening is that this galaxy is falling into the little cluster that is Stephan's quintet from behind, and is smashing into the intergalactic medium in the cluster. And this structure here is actually a bow shock of gas in the cluster that's suddenly heated up, excited, and has started forming stars within the cluster. And you can step through and show how all of this looks in velocity slices. So now I'm doing contours of ionization, H-alpha contours at different velocity windows as I step through. So again, this is this shock lighting up. It's 1,000 kilometers per second thick. So again, I said the rotational speed of one of these galaxies is typically 200 kilometers per second, but the shock wave that's coming through is truly astonishing. And we've done ourselves a bit of a disservice, because we did not expect to produce something quite so complicated. We thought we'd take an image of these two galaxies, we'd get the rotation curves, it would be quite fun, end of story. And what we find is that we've got a whole bunch of people looking at this data, and 4 months later, they're still staring at it, scratching their heads and trying to work out exactly what they want to write about it. It's very, very complicated. And this is all 1 hour of observation with Weave. So the message is that we built something that's very, very complicated and very, very powerful, and we're very happy with it. Again, that's another way of looking at those velocity slices. Sorry, I'm going to pause for a drink because I'm losing my voice. We can also look at neutral hydrogen from the VLA. Again, this is only the pair of galaxies that we're interested in. There's nothing much happening in that shock in neutral hydrogen. Down here in the spiral arm, which is this chunk, there is actually star formation going on and gas flowing in. Up here at the bit that we didn't look at, there's quite a lot of star formation going on, and we think we might go away and look at that in more detail. But here, this is not star formation. This is just shocked ionized gas. We also took some data with the individual fibers from the MOS just to play around. So that field that I showed you at the beginning, again, we happened to observe this very close to the full moon, which was a bit of a pain. But this is now H-alpha. Each line going across here is a spectrum of an individual galaxy. These are redshift 0.3, so they're pretty high redshift. In terms of what we're doing, they're all known galaxies. We're studying them rather than identifying them. This one's 0.4. Again, not a surprise. These two features here are the sulfur lines in this galaxy back here. And what we found was we got really good performance out of the MOS spectra in a very shoddy setup without much effort. And we're very pleased with that. So since then, we've been working on refining the instrument, refining the astrometric performance of it, setting up the spectrograph, and we're getting to the point where we're now very close to really starting the surveys. Which brings me to the surveys. I'm looking at the time, it's 8:20, so I'll try and finish fairly soon, but there's quite a lot of survey material to talk through. So the way we set this up, we started with Gaia and we started with LOFAR, and we said, what else do we build into a survey package based on these two things? And we finished up with 8 primary surveys, which is quite a lot. There are 3 galactic surveys, looking at the Milky Way, looking at the properties of stars themselves within the Milky Way, and looking at the evolution of white dwarfs, which is a serendipitous survey because there's typically only a couple of white dwarfs per square degree on the sky. And if you want to go after all of them that have been found by Gaia, that's about 200,000. You would never get the telescope time to do it. If you happen to be covering the whole sky anyway, and you can put 2 or 3 fibers per field onto the white dwarfs, you can do the whole survey for free. So that's fantastic. And then we have 5 extragalactic surveys. So we'll look at galaxy clusters. We'll look at the aperitif neutral hydrogen star formation interaction. We'll look at stellar populations, so high signal to noise spectra of high redshift galaxies. That's the spectra that I just showed you. There's the main LOFAR follow-up survey, and then there's a little bit on QSOs, which I won't say much about. But the key here is that the LOFAR survey and the QSO survey and the main galactic archaeology survey, they all happen at the same time in the same fields with different fibers. And that's really powerful. It's one of the reasons we built the instrument the way we built it, so that we can do all of these things at once. And the only real problem we have is the dynamic range, because the brightest stars in our fields are typically 16th magnitude, and the faintest quasars in our field are typically 22nd magnitude. And scattered light within the spectrograph has been an interesting problem for the design to try and compensate. We haven't proven that we can do that yet, but it looks pretty good. So we're pretty much fully commissioned. We're still working through some details. Science verification observations have begun, and we expect to start our surveys in August. 30% of the time on the instrument is open. So it's open to sort of classical principal investigator mode observations, which will be time shared. So they'll go into a queue and the observations observe whichever field is most effective to observe at the time. 70% of the time is for the surveys. So over 5 years, we have 1,263 nights of telescope time, and we should be able to observe about 12 million spectra. And I think that's a good point for me to stop looking at the clock, and I'll take questions. I can just skip through. I have a lot of other things, but the map of the sky typically looks sort of like this. This is in galactic coordinates again, so that's the Milky Way. This is the terrestrial equator running through here. This is the Milky Way running across it. This is the high galactic latitude sky where we do our extragalactic surveys, and a little bit in the other hemisphere. And then some very pointed targeted fields and high resolution observations. I won't go into any more detail on that because I think it will take up too much time. But I think that's a good point to stop and see if there are questions.
Thank you, Gavin. Any questions from the floor? And I could remind those of you who are connected via Zoom to send your questions via chat, and I will translate them. Well, not translate them, but read them out. Any questions from the floor?
Did they transport everything by road?
No, because the Canary Islands aren't really accessible by road. So in fact, it's an interesting question, because the corrector is too big to go on a plane and land in La Palma. So the corrector was put on a boat out of Cadiz and shipped down. The spectrograph was put on a truck in Dwingaloo and driven down to Cadiz and put on a ferry and then driven up the mountain. And the positioner, we were going to do the same with the positioner, but we ran into the end of 2020 and the shipping crisis caused by 12,000 containers of PPE in Felixstowe. And in the end, we had to put it in a container and ship it by containerized freight, which was a nightmare because it got damaged. And one of the reasons that was 2020 and now is 2022 is we had to do quite a bit of remedial work after shipping. And that was very annoying. But no, you can't drive it. And we're talking about the equivalent of 4 large shipping containers.
And you then drive it up the mountain.
And then somebody has to drive it up the mountain. I didn't mention the mountain road. The mountain road is the worst road in the world. There are 367 corners in 45 kilometers on the mountain road. Most of the corners are 180-degree corners. It goes from sea level to 2,300 meters in 40 kilometers. And it is actually the steepest island in the world. So a lot of the damage may have been caused by shipping, but enacted by the drive up the mountain.
A question from Andy A.
Yes, the WHT does still have its original mirror. No, we haven't done any extra figuring. It gets recoated every couple of years and it gets cleaned. But no, it's still the original mirror that was made by Grub Parsons.
Any
Image
other
quality is
questions?
very good. Excuse me.
I spent 5 years building it. Must have learned a lot. If you were to build it again from scratch, would you build it differently?
I think you said I spent 5 years building it. I spent 12 years building it. Would we do anything differently? I think there are some little details that we built differently. One of the things that caused us a lot of problems was that the magnetic plate that the magnets are moved around on is made of invar. And for those of you who don't know, invar is a special alloy of steel that has a very low coefficient of thermal expansion, which is great. But if you try to make a big flat surface out of invar, it shifts around like crazy. So its temperature stability is fantastic, but its dimensional stability, it takes months, years even to stabilize after you've machined it. And we need that plate to be flat to 20 microns. So we had to do some very sophisticated aging of the invar, accelerated aging to get it to reach its lifetime, and then we could stabilize it. And now we do have it flat to about 14 microns. That's something I think I would have done differently. So some of the internal structure, yeah, we would have done it a little bit differently, but the basic idea, no, I don't think so. I think it's working quite well.
Other questions? Tony.
You mentioned contra-rotating matter in galaxies. Is it still contra-rotating?
Did you get that, Gavin?
I didn't hear any of that, I'm sorry.
You mentioned contra-rotating matter in the galaxy. Is it still contra-rotating?
Yes, it is. So you can still pick out those kinds of things.
Subsidiary?
What proportion of the total mass of the galaxy is contra-rotating?
What proportion of the total mass of the galaxy is contra-rotating?
Oh, I couldn't tell you that. I mean, that was a simulation of a single small dwarf galaxy. So that would be something like 1 to 2% of the total mass of the Milky Way. So really not a big fraction, and you have to pick these things out.
Any other questions? Sorry, Colin.
Really impressive. What are you going to do next? Are you observing with it, or are you planning your next instrument?
Are you planning what are you going to do next? And are you planning your next instrument?
Well, I'm quite looking forward to spending some time looking at the data that comes off this. But yes, I am planning the next instrument. So as you said in your introduction, the next instrument is a similar sort of instrument. It's a multi-object spectrograph for the extremely large telescope, which is a 40-meter telescope. The instrument is a bit of a challenge because the plate scale is everything. So plate scale on WHT is 57 microns per arc second, our prime focus. Plate scale on the ELT is 3.3 millimeters per arc second. So picking off a single seeing limited or poor AO limited stellar image with fibers is very difficult if you need a 3 millimeter fiber. So we have to do a lot of clever things to change scale and work things down, and everything is massive. It's very, very difficult. And actually, I've been working on this particular instrument since about 2008. And Weave is something that I started as a time filler to wait for ESO to get their act together on deciding what they wanted to do with the telescope. And I've just moved that instrument now into the second phase of design after 18 years. So yes, that's what I'm going to be doing for the next 10 years is working on that instrument as well.
Gavin, thank you very much for a fascinating insight into pick and position and spectroscopy. Thank you very much indeed.
It's been a lot of fun, and I hope you all enjoyed it. What I don't actually have a feel of is how big your audience is, because I can't see them.
It's this one. I've got to share screen.